I hope people online can hear me as well. All right, so my name is Vilasha Mensami. I'm from Ruhr University, Bochum, and I will be chairing the next session, which is IoT. We have two talks, both of them will be online, and we will need to make sure that when you have questions at the end of the talk, please come up to the mic and ask your questions, or I can come to you and hand you a mic. Each talk will be about 20 minutes long, followed by 5 minutes Q&A. And first up, we have Dhananjai Bajpai from Marquette University, and he will be presenting Home Shell IoT Traffic Analyzer. Could we please have the slides?
Yeah, can I share my screen? Okay. Let me know if you can see my screen. Okay, fair enough. I'll start. Hello, everyone. My name is Dhananjai Bajpai. You can call me DJ because my name is pretty long and complicated. I'm going to present today on Home Shield IoT Traffic Analyzer, and I will try to break it down in smaller steps and then have an interactive session at the end of the presentation if required. At any point of time, if you can't see my slides changing, my cursor or my voice breaks, please let me know as soon as possible. That will be helpful. Okay, so the introduction. So we are today living in the world of IoT. Everything is connected and all the devices can talk to the internet. It's a pretty fancy place to be in. But the underlying problem statement is about data ethics and data sharing. So today we go and buy an IoT device, can be a smart TV, a smart plug, or anything that can talk to the. Yeah, I'm trying to do that. Somehow is. Can you see it now? Is it full? Okay. I am trying to make it full screen, but it's just not letting me do that. Okay, one more time. Let me try to share the other screen. Is this better? Yeah, no problem. Yeah, thank you for the update. Cool. So coming back to the problem statement that all the IoT devices that we have an issue of data ethics, data sharing, and data governance, because we feel like IoT devices are just doing something on the front end, but as we analyze the activities of such IoT devices, we also find out that they are doing a lot of things behind our backs, irrespective of who manufactured them. So what was the motivation? As I said, my home is equipped with a bunch of IoT devices, and I wanted to understand, is it a data leak? The goal was to develop a very generic and scalable platform where I can see what these devices are doing behind my back with almost no cost or minimal cost, and then with zero additional hardware. So if I go and buy a smart TV, a smart plug, and I plug it in, connect it to my router, how can I really analyze what are they doing behind my back without connecting any additional resources to it? And before we get into the nitty gritty of it, the magnitude and impact of this research can be summarized. Huawei is a giant manufacturer, but it is accused of installing spying equipment inside the routers. So, and that is a very big research conducted by CNN. You can click on this hyperlink and it will take you to the article. The US government has also banned Huawei and ZTE equipments because they have discovered if you go go and buy ZTE equipment and kind of open it up, you will see an additional Wi-Fi hardware installed inside the router itself, who might be rerouting your data to different servers. Again, you can click the hyperlink to read the report. And very recently, TikTok has been accused of collecting government personal information and sharing it with different headquarters across different countries. This is an ongoing investigation, but the agenda has been to push a complete ban on the app itself. And this is still an ongoing discussion. So, which again brings us back to the bigger problem is my home safe and is it data leak proof? Before I get into what has been done in this project, a very quick overview of the background. So there are similar researches which were conducted by UNSW in Sydney. They made an IoT test bed where they used a Raspberry Pi and connected a bunch of IoT devices, then reconfigured them and collected all their data. It's difficult to pinpoint at one particular papers because if you click on this hyperlink, you will get access to the last 20 papers that are published in exact same domain, and you can also see how they have collected data per day, per month. And you can download that data and actually check how each IoT device is behaving behind the back. The advantage with this approach is that you can actually record each and every packet, the protocols on which that packet is acting upon, and the exact port numbers, and you can get details to a very small microscopic level. The disadvantage is that if you want to replicate this on your home and you want to analyze your IoT devices, you cannot do that because you will first have to go and buy a Raspberry Pi and then actually rewire and reroute your smart TV through the Raspberry Pi and then reconfigure the Raspberry Pi to talk to the internet routers, and so that you can record all that data. So it is not very scalable if you want to apply it into your house. But if you really want to read something about what an HP printer does behind my back, you can actually go and pick up one of their papers and see all the servers that it pings behind your back. So that is what has been done in the background yet. There is always a test bed. There is always some additional hardware where you try to figure out what different devices are doing. My approach was that I don't want to spend anything on the new hardware. I want everything to be a software solution. And for that, I reconfigured my router itself. So in this figure, if you can see, and I hope you can see my mouse pointer, what I've done is there are like different IoT devices which are talking to my router. I went into my router and reconfigured it to an open DNS server. I have steps how anyone and everyone can do it. You just need to get into your router and add a primary and secondary DNS address. And then you have all the traffic going through your router rerouted towards open DNS server. And then there is a Python script which you can deploy to extract all that data and give you actual insights. The advantage, as I said, it is generic, scalable. You can do it on your home, on your devices, and there is zero dependency on anything else. The only problem is that once the trial ends after 15 days, you will have to spend around $20 per year to continue the access to the open server community and to get this umbrella network going. But within 15 days, if you are accessing your smart TV and other resources, you will be able to capture a lot of data, which I was able to get within first 10 days. So it won't take a lot of time here, but this is the step one. You can just create your free account on the DNS. It will give you some of the primary and secondary keys. Take those keys, come back to your router, reconfigure your router, and that's it. This will work on almost every TP-Link router. I haven't tested on other routers, but I'm pretty sure that you can configure your primary and secondary DNS sources pretty easily. So once all that is done and you are good to go, this is how your data will look like. I will come to the insights in the next slide, but this is still raw data. You will need a Python script which will be able to read that, okay, what does node.e2ero.com means? And you can kind of cluster it and make a consumable CSV file, which will tell you that at this date, at this time, this packet was sent to this particular destination, which ultimately is an Apple iCloud application. And then you can parse through your consumable data application by application, assuming some Python knowledge or some data parsing knowledge is there with the user who is doing this type of an effort. Which brings us to the results. So interesting find. So I recently purchased LG Smart OLED TV, and everything inside this green dotted box, if you can follow my mouse pointer, is my voluntary activity. I can power on the TV, I can go to the next state, I can switch channels and enjoy. Whereas in this red dotted line, everything is happening behind my back, which I never knew that my TV is really smart. So for example, I power it on and it will take me to my home screen. I am happy to see my home screen every time, but behind the back, it is pinging to a server called Alfonso. And how did I know this? I mean, I can go back to my data and you can see I'm trying to parse it as per the application, and Alfonso kept on popping up. I never knew what exactly this was until I read about this, which is in the next slide. But on a very high level, Alfonso is a LG ad service. It records almost everything: what you watch, what you listen, what you see, the total duration of it, where you live, what's your location, other demographic stats, and then it shares that data out to 300 other countries, 300 other sources, and kind of makes advertisements for you and sends it back to your home screen. That is what they claim, but they also, if you go to their official website, which I have the screenshots in the next slide, you will also read certain things that it follows standard data sharing practices. And as you buy the LG TV, you have unknowingly signed for Alfonso, which is nowhere written in the claim, but every user who is using the LG Smart TV is pretty much sharing their information with Alfonso. And then let's say you, from your home screen, you go to Netflix and you're happily watching a show. Behind the back, it is pushing logs to Netflix, which it is supposed to, because that's how you will maintain your security details and other sync protocols with Netflix. But it is also pinging back to Alfonso every 10 seconds. And it's doing the same thing. Similarly, if you go to any other channel, let's say Hulu or any other Disney, Amazon, it will keep on sharing information with different ad agencies, and it will keep on recording your logs. Once you power it off, it does pretty much nothing, just goes to a sleep state. And this is what exactly happened. So I used this for 15 days. I switched on, switched off Netflix and watched it 540 times. And behind my back, 310 pings were given to Alfonso, then followed by YouTube, Batch Media, and Hulu. And this is the screenshot from Alfonso itself. You can read it in your free time that it is an LG ad solution. It does advertising over 40 countries, talks 300 different servers. And once you buy the LG TV, you have pretty much signed for Alfonso by default. And it takes almost every possible piece of information that you can generate, every possible digital signature that you can generate, and it just shares it. This is what is collected and shared: your video and audio information, IP address, user location, programs that you have watched, ads that you have seen, ads that you haven't seen, make and model of your device, operating system, the time that you interact with the device, the time that you interact with a particular service, demographic, and all that information gets shared with these data sharing partners. And then these data sharing partners will share it with their partners, and there is an entire supply chain which never stops. So if you have purchased the LG TV, you have signed for Alfonso, and Alfonso has signed with these companies, and then these companies have signed with others behind the back. So once you hit I agree, you pretty much agree with everything. And there is like no way the user can know it unless you have actually seen the data. Okay, long story short, I also tested it on my iPhone. iPhone behind the back always stalks the iCloud, and it tries to keep a sync of all the activities and how many times you have consumed Apple apps, and it tries to push Apple apps on top of other applications. So if you have Google Maps and Apple Maps will take priority, even if you are a frequent user of Google Maps. That is how the iPhone is configured. They will make sure that the ping happens to their services first, and all the ads and whatever you see on your phone is first from the iCloud, followed by any other service. But no other ad selling platform was recognized here. Something similar with my smart IoT plug purchased from Amazon. It talks to the service cloud and just does the switch on and switch off command. There is nothing hidden or fishy about it. Won't take a lot of time on the activities, but you can pretty much see the blue and yellow. This is what it is. The blue and the orange, this is where it is talking the most to. That is where too many pings are going. And this EEROUP, the EROP and the E2RO networks that you are seeing, they are again happening behind the back. So it is a third-party Wi-Fi connectivity platform where they are sharing more details on what is on your mesh network, what devices you are talking upon, what's the load on your mesh network. And if you read about these two links, it will tell you that although they try to maintain your web activities and maintain your network, but they also share your data behind the back. So same story. Once you hit I agree, you pretty much agree with everything. In conclusion, the paper has kind of uncovered and shook me really bad about my smart TV. iPhone surprisingly has a Apple first policy. IoT plug is pretty quiet, does what it's supposed to do. The TP-Link router itself is smart. It talks to a bunch of different mesh networks and shares your information out. So your router itself is not safe. Forget about your TV and other devices. The router itself is sharing out information to other servers about your activity and your packet consumption. Not sure if I have read about the router itself that this is what it is supposed to do, but on the primary level, it just needs a little bit more analysis on what and why they are sharing this information from. The key limitation is that if you want packet details from what port number and what protocol each packet followed, that is a little difficult to get. The metadata is also a little difficult to track, such as packet sizes and other sources. And this is obvious because I am accessing OpenDNS, and they also have some data protocols. They will not let you record these nitty-gritty details. For the future work, this can be extended not only to one smart TV, but different smart TVs, and maybe to for an entire apartment, just to see that is Samsung, Sony, and other vendors are also doing something similar, and is it like an industry practice which everyone knows but nobody's talking about? So thank you so much. I would like to rest my discussion here and open for any questions and feedback.
All right, thank you very much for this interesting presentation. Do we have any questions from the audience?
Yeah, thank you so much. I was wondering if you, because I'm a bit familiar with the database of the Sydney lab, and I know they stopped it, and I wonder if you're planning to do something like that, that it's kind of like a test bed that can be used for other work. And the other question is, have you tried to block all these, because they're basically just IP addresses, and if so, does it impact the functionalities of these devices that you tested on?
Yeah, the answer for the first question is that not planning to create a test bed. That kind of defeats the purpose of making it scalable and generic. I will try to contact with the test bed university lab just to cross-check the results and make sure that what I am seeing, have they seen this before? That's number one. And number two, I haven't tried blocking it. I don't think so that the OpenDNS Cisco server allows me to block something, but I might be able to do it from my router. That's a good point. So I can access my TP-Link router and try to block the Alfonso webpage, and then cross-check if something happens to my TV. Good point, though.
All right. thank you. Do we have further questions? Yeah, please go ahead.
Yeah, okay. Hi, I'm Ruben from Brussels. Like modern smart TVs have this feature, between quotes, called automatic content recognition. Did you try whether that impacts the traffic? Do you see any impact on traffic if you, for instance, just plug in an HDMI cable and then play some video file and then see whether that gets recognized?
Not yet, but that's a good point. I do remember connecting a bunch of USB drives, and that did not lead to any spike. But you're right about the HDMI, because there have been claims that if you can read the magnetic field across the HDMI cable, you can actually access the entire data. So so-called HDMI cables, which claim to be 100% shielded, they're actually not. There are sensors which can read the traffic and recreate that content. So I'm pretty sure that if I connect the same pipeline and I connect my HDMI cable with an external monitor, not really sure is even the external device which is connected to my television is safe enough or not.
Okay, thank you. Do we have other questions? Maybe one from my end. So I was curious whether you also read, so usually there are end user license agreement or terms and conditions that you have to, as a user, agree to before you use a particular device or service. So I was wondering if you correlated your findings with what was written in these end user license agreement or terms and conditions.
Yeah, that is a great point. So once when I went back to the LG's website and I started reading about the agreement, there are like no visible or obvious literature telling you that your data is going to be shared. There are some high-level abstract details saying that your information is critical and this is how it is captured, so on and so forth. But there is no mention of what is getting recorded, to whom it is getting shared, and once it gets to their doors, are they allowed to share it any further or not? So this is what took me by real surprise, that they know what's happening and they also choose not to disclose it in their agreements. And this is mentioned on page number 7 or 8, somewhere in the middle paragraph, which I'm pretty sure that nobody wants to read. Like, you just want to watch your television and get it set up. So yeah, it's a practice which happens openly, and I mean, less of us know about it.
All right. And maybe one final question. Did you also look at the companion apps of these smart TVs, or was this only just the TV themselves?
Just the TV themselves as of now.
Okay, all right. Great. Any other questions from the audience? Doesn't seem like it. So let's thank the speaker once again. Thank you.
Thank you.
Okay, then we can move on to the second speaker. We have Apolline Zehner from ULB, who will be presenting privacy-enhancing technologies against physical layer and link layer device tracking. The stage is yours.
Yeah. Please wait. You should be able to see my screen now.
Yep, we can see your screen.
Yes, that's good. So, I am Apolline Zehner from ULB, and today I'm going to present a study that I did about privacy-enhancing technologies against both physical layer and link layer device tracking. So let's start with a quick example. When you go in public places nowadays, you are about to see like warnings that, for statistical purposes, for commercial purposes, a geolocation system could be used using Wi-Fi or Bluetooth. So here it's in a big shop in Paris, but it's also present in airports in France, for example, or even in Paris subway. So it's quite developed now. And yeah, manufacturers sell that technology as a way to do location tracking, both with Bluetooth LE and Wi-Fi, to track accurately customers, for example, because GPS is not really precise or even not usable inside buildings. So combining those technologies allows those businesses to create customer profiles that are supposed to be anonymized, to track customer movements, to know which parts of the shop are the most interesting for customers in real time. So that's the commercial version. However, you only need a few anonymized location data points, like only 4, 5, 10 data points in the same shop to be re-identified the next time you go to that shop, because our behavior is predictable and is quite unique. And also there is data brokers. You might have heard of them, that sell anonymized data points, location data points of people across the globe, from apps, for example, but also from those kind of Bluetooth beacons and Wi-Fi location trackers. So it could allow identification of specific people, and it could be harmful in some cases. So yeah, it's not only commercial. Those kind of this kind of tracking works in two ways mainly. So you could use probing requests. Probing requests are when a device is searching for Wi-Fi or Wi-Fi networks or Bluetooth devices that are already known and trusted. For example, if I am in a train, my phone might be searching for the Wi-Fi network of the train, but even if I'm not on the train, it will still be searching for this network. So it could be unique data because you also have your own Wi-Fi network, for example. And for Bluetooth devices, especially for IoT devices, those devices are sending quite regularly advertisement data. For example, sensors like temperature sensors, sport sensors, etc., are regularly sending data. So it's broadcasted, meaning that everyone around the device could listen to it. It could be your phone. It could also be a third party, and it could also lead to some kind of fingerprinting. So there was a first solution that is used even nowadays because it's quite useful. It's to randomize MAC addresses. So MAC addresses are the physical address of both Wi-Fi, Bluetooth, or even Ethernet devices. It's implemented since like a decade now, at least for Apple devices. But Google, for example, only enabled it by default 5 years ago. even if it was implemented in 2017. And so could we still be tracked even through these countermeasures? So first of all, we could have implementation flows that could lead to de-anonymization and so to re-identification of a specific user. So there was some flows like the use of sequential sequence numbers that are in data sent to every device around, even if the MAC address was randomized during the at a point. Sometimes devices are also sending data with their real and physical address and not the randomized one. That's quite a flaw. But we could also use fingerprinting because devices are not using standardized payload. And so you could, for example, identify a specific kind of device, and it could be already a good starting point to identify someone. So how could I get a device to relay its real MAC address? And so how could I trick it into de-anonymizing itself? As I mentioned earlier, devices are probing regularly for Wi-Fi networks that are already known, and some Wi-Fi networks are open, like trained Wi-Fi networks. So for example, in the TGV, you have SNCF Wi-Fi anyway. And so all you need to do is to set up a rogue IP. So Wi-Fi access point that uses the same Wi-Fi network name that will receive a lot of connections. And so when a Wi-Fi device is connected, it was using its real MAC address after being connected. And so it was an easy way to de-anonymize like Wi-Fi devices. But nowadays, most of those implementation flows are patched. Devices are now randomizing their sequence numbers. So yeah, when they are changing their MAC addresses, they are not following a sequence, and so you can't use that anymore. And they are also using randomized MAC addresses when connected to Wi-Fi networks, at least to open Wi-Fi networks. So those that are most likely to be faked. But we could still use some kind of fingerprinting, maybe, because we have a lot of metadata. For example, you have the MAC address randomization time interval, so how much time is in how much time a device is randomizing its MAC address. You could also use its emitting power if you are close enough to the device, or at least that the device is static and your listening device is also static. You could also use device-specific information because those data are not standardized. Well, in theory, it is standardized, but it's not well implemented even nowadays. And so let's start with MAC address randomization through time, because, for example, in Bluetooth devices, you don't have a standardized time interval for MAC address randomization. And you also don't have some kind of randomization of this time interval. So it means that in some cases, you could de-anonymize the device through its randomization time interval, because it could be quite unique, even if most devices are randomizing their MAC addresses every 15 minutes. It's not the case of every device. Also, it's really unlikely that a device will randomize its MAC address at the same time as another one, except if you have thousands of devices in the same area that you're able to listen to. But in most cases, it's really unlikely. And so by both combining the randomization time interval and the fact that devices are not randomizing their MAC addresses at the same time, you could de-anonymize a device and thus a user. You could also use the RSSI, so the emitting power that is received by your listening device, because even if those devices are randomizing their MAC addresses, they are still advertising themselves at the same frequency, like at the same time interval. So yeah, you still have some data that you could use, and the emitting power is unlikely to change during the randomization process, because, well, advertisements in Bluetooth LE, for example, are sent every 100 milliseconds at least, but it's the order of magnitude. So in a few milliseconds, in a few 100 milliseconds, the device won't move that quickly to have an emitting power that changes drastically. However, RSSI is quite useful to de-anonymize and tracking devices, especially in cases where you don't want to be tracked. For example, AirTags used against domestic violence victims or survivors, because some papers, like the papers from Depressional, are using the RSSI, so the emitting power, to de-anonymize and fog out those trackers, because you could make a customized tracker that is not trackable by Apple or by Apple apps. But we could use some countermeasures. So first of all, we could randomize the emitting power. So we could also randomize at the same time the received power by the listening device. However, it might lead to performance issues, because if you randomize the emitting power, you could be in a case like in a space of a few seconds, you can't use your headset anymore, for example. So it's quite tricky to implement. You could also reuse MAC addresses that you generated before, because as for now, research is mostly focusing on the fact that MAC addresses are changing every few minutes, every few hours, but not considering the fact that a MAC address could reappear at a point. It could be an interesting countermeasure. You could it could also be interesting to introduce CN periods. So periods when the device is not emitting anything. For example, after randomizing its MAC address, it could not be not emitting for a few seconds, like for a randomized period of time, to decrease accuracy of those de-anonymization methods, because those methods are mostly based on the fact that the device is constantly emitting and are not really taking into account the fact that the device could not emit for a few seconds or for a few minutes, but it could also lead to performance and usability issues as for the emitting power randomization. And to finish, we could minimize the amount of data that is sent because the manufacturer-specific information, for example, can contain unique identifiers. So even if the MAC address is randomized, you are still able to track a device because the randomization was not really done in for the work device, but only for the MAC address. And so, yeah, there is new possibilities, new opportunities to research. So metadata-related attacks are not well researched for now, and combining those with existing attacks. So attacks that are mostly based on implementation flows would reduce the effectiveness of existing countermeasures. But those metadata-related attacks could also be used by themselves. We could also just reduce metadata or even just randomizing it, because it could really impede tracking, even both through existing attacks and upcoming attacks. But it could really cause problems with devices usability. Like your device could be disconnected without any notice. And the upcoming research should really consider full applications of those de-anonymization techniques for AirTags, for example, because AirTags are nowadays really used to track, for example, domestic violence survivors, or even just without consent. So yeah, research should also take that into account and maybe find ways to identify those devices without impeding too much on users' privacy. And yeah, I'm currently planning in my lab to try those metadata-related attacks in crowded environments, because as for now, it's mostly done in controlled environments with a few devices in small areas, and it will allow us to measure the effectiveness of those attacks and of those countermeasures. Do you have any questions?
Great, thank you very much for this talk. We already have one question.
Hello, I'm Debojyoti. I have a question related to, not exactly related to the talk you have presented, but slightly different. So for example, in the talk, you mentioned different kind of attacks, and then different kind of possible countermeasures. But it feels like there are those countermeasures are specific to those attacks. So have you tried to analyze if there are commonalities among those attacks or commonalities among in those countermeasures? For example, you see that all these several attacks have this common property, so that countermeasures, as long as they achieve this common property, could prevent this attack. So have you analyzed or observed any such commonalities?
As for now, I didn't analyze such commonalities, but it could also be an interesting research subject for the future. So thank you.
Thank you very much.
I also have a question. So it seems like one of the attacks that also very hard to think of a countermeasure is the emitting power, and it seems like it's very efficient attack. And the other papers that they are proposing that we can randomize the emitting power, A, it will decrease the usability of a device, and B, it's very draining in terms of energy. But did you look at these papers and can think of a way of randomizing the emitting power according to certain needs? Like, for example, if I am at my house, maybe I don't need to randomize this. If I go to a hospital, I don't want to be identified, I can use it. And in those combination, how effective is these countermeasures? And do you think even if it's effective?
It could be effective, in fact. However, I tried recently to randomize the emitting power, and I found out that current attacks are still able to identify a device, even if the emitting power is really randomized. So not just at the margin, you know, but it could be an useful way to impede those attacks. The only problem would be, I think, that your device has to know that you are in a specific place, and maybe device manufacturers could use this data for their own purposes as well. But yeah, it could be an interesting subject also.
All right. I actually also have a follow-up on countermeasures. So do you have any thoughts on who should be responsible for deploying these countermeasures?
I think it mostly has to be device manufacturers, because, for example, they are not randomizing or even reducing metadata that is sent and broadcasted to everyone around those devices. But it could also be like through, legal ways, like in Europe, for example, the European Union or countries, because it's related to privacy. So maybe legislation could also help to force manufacturers to implement correctly those randomization protocols.
Okay, yep, great. Any other questions from the audience? Okay, I don't see anyone else with questions, so let's thank the speaker.
Thank you.
And this concludes the IoT session. I will now hand over to the next session chair.
All right, just a second. All right, and so that brings us to the second session of this track of Impact. So this is the Mixnets session, and we have two exciting talks lined up. So to start, the first one will be by Harry Halpin from NIM Technologies, and he's going to tell us about unifying privacy and AI, why he's an Entropist. All right, Harry, please, the floor is yours. Harry, you're muted. I think we can see you talking. Okay, there we are.
Looking good? The slides?
Yeah, we can see your slides. Everything is good.
Cool. Okay, so This is a more of a position paper. It's not really, there's no particular new research involved, but I think we're trying to motivate why people should be interested in mixed networks. So as folks in anonymous communication may know, the field of mixed networks and anonymous communication is quite small. And to be honest, the field of privacy enhancing technologies itself is quite small, particularly when compared to large fields such as artificial intelligence. So AI, which is a bit of a buzzword right now, is making huge gains and strides. And there's just simply not enough people working on privacy enhancing technologies. And I kind of wrote this paper trying to figure out, well, why is that? And why are privacy enhancing technologies needed? And how can we bring the field forward? And I subtitled the paper, Why Am I an Entropist? Because I end up, just to give a brief explanation, I end up arguing for a return to taking entropy of various sorts more seriously as a metric, primarily because it's one of the primary metrics used in AI research. And it lets us compare both our systems internally in privacy enhancing technologies. It's a pretty good way to compare the success of system A versus system B in some particular problem. And it also allows us to compare our systems against artificial intelligence-based systems, which are essentially classifying or generative discrimination systems. So let me just explain quickly. So I was an academic, but now I'm doing mostly industry, commercial work. So I did my PhD in artificial intelligence. My PhD is not in cryptography. So I apologize if I make any mistakes. And I used to work on web standards involving cryptography and lead research at Universite Paris. Right now, I'm working at NIM Technologies for all of you who want to try out a cool new Mixnet app. You can actually download NIM VPN, which is a Mixnet, which is easy to use as a VPN from your favorite app store. But to the more theoretical topics, I think that the primary argument I want to make is that artificial intelligence systems effectively are a kind of dark inverse of privacy enhancing technologies. On a very large scale, what almost all AI systems do, there's some exceptions, but they're kind of marginal right now, is that AI systems effectively minimize entropy in noisy data to discover information, new patterns, to create, classify, discriminate against certain existing patterns, and to now, as known through, of course, ChatGPT, generate new patterns. The underlying patterns are getting coded statistically. You can create probabilistic generative models to generate new kinds of patterns. It doesn't really matter what the data is. That's, to a large extent, what AI does. The only systems I think that kind of avoid this definition are a lot of systems in what you would call good old-fashioned AI or symbolic AI, where essentially they were operating via various forms of automated theorem proving or knowledge representation languages. And these systems don't scale, they don't really work. And most of the kind of research in AI and deployed systems are now effectively statistical-based systems which deal with entropy and distributions of all sorts of data. On the other hand, in contrast to AI, privacy-enhancing technologies can be characterized by the addition of entropy, or maybe easier to think about it, noise, which obfuscates information in existing data. So, I include a very broad definition here because I also want to include deleting data, removing data, minimizing data. But effectively, when you minimize data or you delete data, you, to a large extent, increase the entropy in a particular data set. So just to go a little bit deeper, that's the paper right there. But I kind of discuss a little bit more of the implications of this. So you really want to go into what AI is. I think one of the best books on AI is by Brian Cantwell Smith, who's a philosopher comes from computer science. For people that use reflection and programming languages, he invented that technique. And he says, well, why does this work? Why is AI working so well now and not in the past. I think it's worth repeating this quote. What is transformative about the present age is not just that we have access to mountains of data, conceptually represented facts, text, Wikipedia, Wikidata, so forth and so on, with predictive and analytic power enabled by their ability to track correlations and identify patterns in massive statistical detail. But what is transformative is we don't have to force fit those patterns of relation into a small number of conceptual forms. So that means often, and this is what appears so magical about AI, particularly to users who are not familiar with the technology. It appears that ChatGPT is intelligent. It appears that speaking. It appears that it can recognize all sorts of patterns over data and movies and images and create new kinds of movies and deepfakes and whatnot. What's really interesting is that a lot of those patterns that it's finding using these essentially, billion, if not trillion, node neural networks, which is a vector space, which is almost unimaginably large, and is that a lot of those patterns it's finding are non-conceptual. We, the users, can't really identify and state in terms of logical facts or even a clear analytic mathematical equation what exactly is going on. We'll go into this in a second. But we know it just works, that somehow, after capturing enough data, what's remarkable is that we thought it would work less and less well, but actually just increasing the parameter space of these systems to absolutely gigantic numbers has somehow reached there's been some sort of qualitative shift where they seem to actually work well enough to fool people into being intelligent. So we have to really think, what is it that's actually happening here? And what's actually happening, particularly if you take the lens of information theory out, is AI can be thought of as nonlinear function fitting for just arbitrary functions. And the function is, of course, the signal, and everything else is noise. And this has been true for a very long time. If you look at older AI textbooks, I'm a particular fan of David McKay's Information, Inference, and Learning textbook, which is free online. And it actually outlines all AIs, at least at the time, all AI systems that were not symbolic based in terms of information theory. And so you see that even today, if you're doing old Bayesian modeling, which isn't done too much today, the way you choose choose the priors, you just choose the distribution with the maximum entropy. That's why they're called max entropy classifiers. But even in AI techniques which don't seem to depend on entropy, let's look at something like decision trees, often used in what's called quote unquote fair and transparent AI, where humans can interpret it. The clustering and the slicing of those decision trees, even if they bottom out in human understandable facts, is usually done in a way such as trying to kind of minimize the entropy over the data set, right? And why are neural networks so successful? When I was a PhD student, neural networks had a bad reputation. They were considered black boxes. No one really knew what they did. But there's some very elegant mathematical work, starting out of Sybinko 1989 and continuing, as I point out in the paper, really until the present day, getting more and more extensive, based on what's called the universal approximation theorem. And the universal approximation theorem, via proof by contradiction of all things, shows that a sequence of neural networks, in particular sigmoid functions, are in theory capable of capturing arbitrary functions for anything from image recognition, natural language, as long as that kind of arbitrary function is indeed mathematically characterizable. Formally, given a family of neural networks for each function from a certain kind of function space, there exists a sequence of neural networks from the family such that the combination of these neural networks, which can be considered layers to some extent, can generate F. So you can see this is your classic neural network here. On the side, you have inputs coming in, you summate the weighted outputs, you kind of throw them to some sort of threshold activation function, and then there's the output. And that's how neural networks worked for a very long time, up until the Rumelhart and Hinton, everyone kind of invented backpropagation. But effectively, what's interesting about these proofs is what they don't tell you how to do. These proofs, these kind of proofs that neural networks are magical function filters can fit any function. They work well in theory, but there is no guarantee that such a neural network actually exist in reality. So they exist in theory, but not in reality. So theoretically, there must be a neural network which can simulate this, but there is no guarantee of the neural network existing, of how to build it. There's no guidance the formal theorems give you of how the network should be structured, how many nodes should be on the network, the layers, any other guidance. And that's why neural networks had a bad name. And the answer ends up just make the neural networks really big, make those parameter spaces huge, and train it with lots and lots of data with some form of error correction, such as backpropagation, where the predictions are somehow, this requires has to be some ground truth of training data, or if you can reduce the trained data properly, reinforcement learning and some sort of policy also works. And again, as we already pointed out, most of the cases of training AI, and I found very hard to find cases that aren't, can effectively be reduced in entropy. So we have this proof that we can detect any function and any amount of data, at least in theory, and in practice, you have to feed more and more data to the machine, and that gets you what these kind of entropy minimization techniques, eventually some kind of working system where, working is often unclear, but it seems to be working, even if we can't understand or explain why it's working. There's a kind of problem here, obviously, which necessitates a revival of privacy-enhancing technologies, because effectively, how all these neural networks work is, again, they require training data. They require more and more training data to solve more and more complex problems. So they approximate this open-ended class of functions. And that requires mass surveillance. And maybe mass surveillance isn't even the right word. It just requires a generalized surveillance apparatus. And the more data, the better. So they have to keep capturing more and more data to feed these machines. And this effectively leads to increased amounts of surveillance and increased attempts to predict and control human behavior. And while people may agree or disagree about whether artificial intelligence will eventually lead to artificial general intelligence, human-level capabilities, superintelligence, maybe it's all for the good in the far distant future, I'm quite dubious of these philosophical prepositions. I think they're a bit hysterical. Nonetheless, what is obviously clear is that AI is leading surveillance and mass behavior and prediction and worse control is a threat to human autonomy. And that's something that requires us creating more and more privacy enhancing technologies. And privacy enhancing technologies can then be thought, and I think this is my kind of general insight. I haven't formalized it yet, but I'm working on it. I'd love to hear what people think. But I think you can generally take pets and you can think about them as noise generating networks. And I know it seems a little silly, but I think there is something there that privacy enhancing technologies can be just as general purpose as AI neural networks. And for anything that AI can do, there should be a corresponding pets technology which can reverse it. And so the way you want to think about it is almost too simple. If you look at a neural network, how do neural networks work? They're just layers of nodes. And in each layer, they kind of do this, again, they try to classify or generate, depending on which way you're running it, some data. And they do this creating the data in smaller functional units. That's deep learning to some extent. And that's what they do. So mixed networks are essentially almost can look the same, right? Just as a neural network has a stratified topology with different fully interconnected layers, mixed networks, particularly at least of the kind of Lupix design, also have different layers, with different mixing at each layer. And each layer is, again, fully connected. Doesn't have to be, but why not? Fully connected to each other layer. And I think it's really the same thing, but it's running in reverse. So what a neural network is doing is essentially each hop in the neural network, similar to each connection, each hop in the mixed network, similar to each connection in the neural network, while neural network is minimizing entropy, taking away a bit of entropy, not, bit by bit. A mixed network, the messages or signals at each hop of the network have some entropy added, right? There's either fake traffic added, traffic can always be dropped, and it obfuscates very important data, particularly timing data and volume data. And timing and volume, of course, is what kind of gives you statistical distributions in general for many common problems. Now, I'm not saying neural mixed networks are perfect. They're still just one tool among many. But what I think is they're actually, what we want is we want something that isn't really a mixed network, but something much wider. So I call this a noise generating network. So what you do is you can just kind of inverse the universal approximation theorem into being what I consider a universal obfuscation theorem. For each function, there exists a sequence of noise generating networks such that we can add noise to each neural network, so that for each kind of function, for each neural network, there's a certain amount of noise, which makes it impossible to approximate that function with enough noise added. So again, what you're doing in approximation technologies in general is you're obscuring information via noise. And we give noise, we don't think about literally, very broad sense, increasing entropy. We're deleting attributes, for example, individuals or other attributes from a database. We're changing patterns via mixing. We're deleting attributes such as time from the data itself. Or we're adding new noise, right? Fake individuals, cover traffic. And therefore, I think there's, differential privacy seems quite similar to entropy-based approaches to privacy. But actually, if you look at the original differential entropy papers, particularly Dwork's work, but most of the other works as well, and particularly all the different metrics which have come out of differential privacy, you see that most of them, they end up explicitly grounding the theory out in entropy. So they're not really building a different science. And this leads us to entropy. Is entropy a good metric or not? And to be honest, a lot of people don't think it is. I think it's a minority of people, primarily from the mixed networking space, that think entropy is a good thing to do. And I agree. I think it is and fundamentally should be a metric we should support. So I want to revisit this debate. The primary debate was, okay, I'm going to speed up a bit here. And again, a paper called Why I'm Not an Entropist by Paul Syverson. We had various arguments against what he called entropism. And entropism, Paul said, is not just entropy in general, it's the use of entropy as the meaning, the criteria for anonymity, or how anonymous something is. And we shouldn't use entropy, Paul argues, because it does not capture everything important. And I do agree, entropy is not a perfect metric. It's what I call metric of the other more useful metrics can be reducible. In the latest survey of PETS technologies, we have over 80 different metrics going around in PETS. There's so many, they're mostly incomparable. So why don't we try to, so obviously it's not necessarily always fit for purpose, but it's a kind of fundamental metric. Paul also argues that it gives enemies a target, your adversary. Entropy provides your adversary with an explicit target that he can then assign available resources to overcome. Furthermore, entropy, Paul argues, can often be measured in the real world. And I do think he's right here. And metrics, he thinks, for anonymous systems should not, I'm just quoting Paul, depend on the values of variables for which we cannot make adequate or predictions. For example, the numbers of senders or receivers of a message in Tor. And Paul, of course, co-founded Tor, and Tor is a wonderful system, and Paul's a philosopher and a genius, so I'm very scared to go up against them. But I do think that he's maybe selling entropy a bit short. In particular, I would say there's numbers of good arguments for entropy. I want to say, in particular, I think what's kind of motivating Paul is that against the kinds of adversaries networks are good at, Tor isn't very good at. And that's global passive adversaries that can monitor the whole network. And while global passive adversaries seemed very unrealistic in 2000, the Tor paper was 2005, I think, and work began a few years before. Today, the world has changed. Computation is cheap. should not be assumed that adversaries finite monetary budgets. Of course, we can talk about computational bounds that take 1,000 years, like in cryptography, but now, let's sure, there's now very powerful supercomputers that are very cheap. So I think we should assume that, an adversary can observe all aspects of the system. That the global passive adversary, particularly as we learned from Snowden revelations, is an important threat model. It's not paranoid, it's not unrealistic, it's what we're actually up against right now in privacy enhancing technologies. And with AI, it's only going to get worse. Furthermore, entropy can be measured. Just because you can't measure something doesn't mean the adversary can't. An adversary, such as the NSA, can certainly determine the number of messages, senders and receivers of messages inside Tor, right? They can monitor because they have more computational money and computational power, more memory, more money, much more of a larger budget, at least until Trump nicks it, than Tor does, right? So just because you can't measure something in a scientific paper does not mean the adversary can't measure it. And lastly, I agree, it's not perfect, but science needs metrics. And entropy seems to be the best metric we have, both for creating a unified foundation of privacy enhancing technologies and a comparative metric. And you see entropy all over the place in anonymous communication, location privacy, so forth and so on. I can't think of a better metric or more universal one that works well across very diverse elements of pets. And also, it's how people often measure the performance of AI-based systems. So we can use the same metrics. So that's why I think I am actually an entropist. And I'm arguing not just that we should think about pets fundamentally in terms of entropy, because that lets us compare ourselves and fight against AI systems, but that the global passive adversary with active capabilities, of course, is a realistic threat, and entropy is a pretty good way to talk about that threat. So that's it. Are there any questions? And I'm happy to take them. Sorry, I'm not there in person. I'm in Europe, but that's my email, and I'm happy to answer things by email as well. Thanks a lot.
Thanks for the great talk, Harry.
Okay.
Any questions in the room? All right, I think we have a question here.
Yeah, I have a question. Aaron Johnson, US Naval Research Laboratory. I'm wondering if you have an opinion about kind of worst case versus average case metrics. I didn't see you define entropy in any privacy preserving system here, but you could define it in a few ways. And the one that I typically would see it in a mixed paper is sort of the average entropy overall messages that are observed, of course, but that doesn't imply that there's some message for which there's zero entropy. So I'm wondering if you have an opinion about a worst case versus average case for entropies.
Yeah, I mean, average case is what people tend to measure, and I'm not against that, right? So you can also, but entropy's quite, so while Mixnet researchers tend to focus on average case, if you look at, for example, it's cited in the paper, there's a whole stream of work trying to basically, best case measures and worst case measures can often also be thought of in terms of entropy. That's how, for example, we got Shannon perfect secrecy. That's how we get weak signature systems based on entropic, what I think Dotis calls entropic signatures. So I think average case is something we should look at. We should also look at worst case, of course. And on some level, I'm arguing for kind of worst case level adversaries, but I do think they can all fit within an entropy-based framework.
Okay, well, if there's not another question, I have another question.
Go for it.
Which would be a question of priors. In order to compute entropy of a posterior distribution, you need a prior distribution. So you could pick the easiest thing, which would be uniform, but I would assume no adversary has uniform distribution. Everybody knows something. That's information. So what is your opinion on the issue of picking a prior in order to evaluate the entropy, the posterior entropy?
Yeah, I mean, this is where I think actually we could learn quite a bit from AI-based systems. So how AI, how general deep learning, any kind of neural network-based system works, try to assume very little in the beginning, and as you learn from data, assume more and more, right? And so that was the example of Bayesian inference, where you don't really know what's going on. So when you don't know what's going on, just assume max entropy as a prior. It's pretty stupid, but actually works reasonably well. However, as you basically learn more and more, you can basically get closer and closer to realistic amounts of encoding of knowledge. Now, that knowledge itself may not be easily encodable as a clear distribution, but I think we should effectively, and that's what we've been doing at NIM, and we're of course looking at the work on Tor as well. That's why I think we should, when we're building these systems and attacking them, having adversaries that have huge budgets and use deep learning techniques with training data over large stretches of time is probably the way to go. And that's kind of bad news for mixed networks, because in practice, with a long enough period of observation, it's very hard to beat neural network based learning. All the mixing you can do in the world, all the cover traffic you can do, get broken pretty quickly. There's of course Claudia's paper on mix match on that front. We have some other papers coming out. We're looking at kind of how much data has to be gathered in order to break certain systems. So I do think it's particularly, and what we've discovered is that mixing itself has very little effect, that it's very easy to build priors, which basically take the mixing into account and then de-anonymize the mixed network. However, what is interesting is then you actually need to move away from mixing, and mixed networks may not even be the right word for what we want to build in the future. And systems, I think in Tor you have, what's it called? Tamarack from Ian Goldberg. And in mixed networks, you have, of course, this kind of flooding of the network with cover traffic and Poisson-based traffic and various forms of noise. And this ends up, we think, actually being much more effective in defeating neural network-based adversaries, which have, again, I think, realistic priors in terms of they learn the actual prior from longer observations of data.
Thanks.
Thanks, Harry. Unfortunately, there's a lot more questions and discussions to be had in the room, I think, but we have to move on to our next talk for the day. But thanks again, Harry. Everyone, round of applause.
Okay, well, do feel free to email them off, and thanks for the question, Aaron, and everyone. Take care.
Thanks. All right. And for our next talk today, it's going to be by Debjyoti Das, and our talk's on Mixnets on a tightrope, quantifying the leakage of mixed networks using a probably optimal heuristic adversary. Deb, floor is yours.
Hello, everyone, and Harry. I agree with you that we need strong measurement techniques for anonymous communication, but I don't agree that should be entropy, because I'm going to present something better. So this is a joint work with Sebastian Meiser, Maurice Kriske, Esfandiar Mohammadi, and Aniket Kate. So basically, this is we are trying to propose a new technique to provide measurements for anonymous communication. So I think most of you know what anonymity is, but still let me just reiterate that this is the state of not being identifiable among many subjects or individuals, so that you can have freedom of expression, avoiding from detection, retribution, embarrassments, etc. So this is one of the tools to achieve privacy, but privacy can be much more than just anonymity. Generally, we talk about different kind of anonymity notions. For example, in case of sender anonymity, the sender Alice wants to send a message to, for example, journalist Bob without revealing her identity. Probably Alice is a whistleblower, and she wants to be She wants to hide among many other individuals. And here we are protecting the identity of the sender. Similarly, you can define recipient anonymity, where you want to talk to some service. For example, you want to send information to WikiLeaks, but probably WikiLeaks does not trust everyone who wants to talk to WikiLeaks, and that's why you want to send information to WikiLeaks without actually knowing WikiLeaks IP address or the physical identity, or any other hidden services, for example, in Tor. And then here we are protecting the identity of the recipient, and that's why we are calling it recipient anonymity. For this work, I will mostly talk about, implicitly, I will talk about recipient anonymity, but also this work applies to sender anonymity. And there are protocols that can achieve these properties, but I'll show specific mixed examples in a few minutes. We have seen what anonymous communication is. Now let's talk about some motivations. Why actually we started doing this work? What's the motivation behind them? So typically for anonymous communication, there are two major or two dominant ways to measure anonymity. One is entropy-based approach, another is you actually do a proof. You show that the protocol achieves certain security properties, and those security properties implies anonymity guarantees. However, they both come with pros and cons. let's talk first about entropy, since we just heard about entropy. It's basically relatively simple to do. You just run an experiment. Not deploy exactly, but you simulate a protocol, an instance of the protocol, and then you experimentally evaluate how much anonymity is achieved. So you don't need to do any rigorous proof. It's basically the experimental result is how you derive the anonymity guarantee. So that seems simple, but then the question is, how do you know that the experimental setup has captured all possible attacks? The adversary in the experimental setup actually considers all possible leakage. We don't know. We don't know if the adversary that we are considering for the experiment is actually optimal adversary. It has captured all leakage. So it's kind of somewhat some confidence that the protocol is actually mixing messages or hiding which message is from whom or to whom, but we still cannot guarantee. And also, how do you bound the sampling error? So for example, you have to simulate a specific instance of the protocol with specific parameters, with specific user behavior. And that means that probably could be favorable to the adversary, that probably could be favorable to the protocol, and we don't know what's the sampling error there. And then we cannot say if the protocol works for, even we run for 1,000 or 10,000 experiments, still we don't know how good, what the quality of the measurement is. And that seems to be a difficult problem with entropy. And then anonymity proofs. Of course, those are strong guarantees. You actually mathematically show that they achieve certain guarantees, but generally difficult to achieve. Let's look at some examples. Not before the example, why this is difficult to actually derive those proofs is mainly because you have to consider posteriori biases. So even though you consider that there are two challenge users, one of them sends the challenge message with 50% half probability, but the thing is, once the adversary observes the network communication, then there is an inherent bias, in the sense that the adversary sees that this link has 1,000 messages, this other link has one message. So probably the message, if the challenge message has entered this node, the message could have gone to the upper link with probability 1,000 over 1,001 and lower link 1 over 1,001. And that gives a bias to the adversary. And when you actually derive the proof, when you actually want to do a proof, you have to consider all such biases. Even for this simple example, let's consider U0 sends a message, and U0 could send the message to either R0 or R1. If the adversary observes this, the adversary knows that there are 5 ways that U0 could have sent this message to R0, where there are only 3 ways U0 could have sent this message to R1. And there are total 18 ways to observe this observation, and only 8 of them are the cases where U0 could have sent the message to R0 or R1. And that means there is an inherent bias. And then if you consider a complex network, you have to consider such biases on all links, on all nodes, all possible randomnesses. And that's why the proofs are inherently difficult. And then, of course, how do you easily quantify this bias? That's the main problem that we face when you try to derive these proofs. There are certain attempts, example attempts, for example, karaoke. They did show proof of anonymity for large networks. However, they did not consider these different weight links, weights on different links. And that led to an inadequate proof. So for example, they considered a gadget. What do I mean by gadget? That means if this gadget is satisfied, they claim that this is sufficient condition for anonymity, sufficient condition for mixing. So that means if this gadget is satisfied, those 2 messages are shuffled. And the gadget is something like the 2 messages are A and B, and they are basically meeting with some noise messages N0 and N1, and then they are swapped. So basically, after they met with noise messages, then they met with other noise message. And in that case, they claimed that this is sufficient to achieve anonymity. It seems so from a first look, but the problem is, what if these link weights are different? If one link has 500 message, other link has 100 message, then immediately this is not a 50-50 chance anymore. and then the gadget is actually wrong. And then any other protocols which are related to karaoke have similar kind of topology, similar kind of network structure, similar kind of parameters, and they also face the same issues. So even though people have worked on these protocols for a long time and they try to do the proofs, and still we find inaccuracies in proofs every day. And similarly, this protocol doesn't have any apparent issues with the current proof, but the proof itself relies on something called square network. That means if there are n messages, you have square root n, exactly square root n nodes, and each node receives square root n messages on each layer. And additionally, they require that all these mixers, I'm calling them nodes, but all of them are honest. Of course, that is difficult to achieve in practice. So what they do is, instead of one single node, they have a cluster, and the cluster has 32 servers. So basically, that ensures that with high probability or overwhelming probability, each mixer is honest. And that means even though theoretically this could have provided us a really nice protocol, really strong protocol, we have if we have 10 layers of 10 total layers, that means we have total 32 times 10, 320 servers each packet has to go through. And that means you end up with end-to-end latency of 30 minutes or something. I have mentioned this. So also to achieve a square root n guarantee, then they have to have a load balancer, which is kind of another server. So that's why it's really difficult to achieve this kind of restricted configuration in practice. And then the question is, can we relax this square root n assumption? Because in reality, you might not have a load balancer. You might want to support source routing. Can we relax this square root n assumption in that case? And is it possible to tolerate some corrupted nodes? So instead of having 32 servers in one node or one cluster, can you make it, for example, 4, so that we have only small percentage of corrupted nodes, and then can we still derive guarantee? And it seems then we don't know how to do the proof. And then we said that we want to do something which is a hybrid of experimental evaluation and theoretical proof. So can we achieve provable guarantees through experimental evaluation? That's the question we wanted to answer. And that means when it requires mainly two things. First, when you are doing the experimental evaluation, you have to ensure that the adversary we are considering for experimental evaluation is actually optimal adversary and efficient, because you have to be able to run the experiment. And then we have to find a way to bound the sampling error over multiple samples. If we can do these two, hopefully we can achieve a technique to measure provable guarantees without actually doing the proof, rather than running experiments several times. That's the hope. So before I talk about actually how we derive the optimal adversary, let's talk about a trivial optimal adversary. So what it does is, every user has randomness steps. For every randomness options, every user, every node, the adversary actually simulates the protocol for all possible randomness values. So in principle, the adversary will run exponential number of simulations to count all possible choices. Suppose, and then the adversary counts those number of choices that actually leads to a specific observation that could break anonymity, or that could that the adversary is interested in. And then basically the number of instances leading to the observation and the number of all instances is basically ratio is the probability. So yes, that works, because that's trivially basically you are counting all possible cases and simulating all possible cases. But you cannot use it in practice, because even for n users, probably you will, if there are k hops, you will probably incur n to the power k, or k to the power n number of simulations. I forgot. Okay. So we need to define an efficient adversary. For that, we decided to use a heuristic adversary. So instead of counting all possible scenarios, we are basically propagating the probabilities. this is kind of similar to what is done in entropy, but with subtle differences. Here, we are first choosing the observation, and then for that observation, we are trying to propagate the probabilities over the edges and nodes. And then basically that means for each layer, the adversary is just propagating the probabilities instead of actually simulating the protocol or simulating all possible cases. And that's why this adversary is actually efficient. You can run this adversary in reasonable amount of time, depending on what you how you define reasonable. This is non-trivial, not counting everything, but still it's usable. Then the main thing we do is we show that this heuristic adversary is actually optimal for sender anonymity and recipient anonymity notion. And that means you know that the adversary is optimal. So that's the first part done, that we need an optimal adversary. And then we show upper bound and lower bound on the adversary, mostly bounding the sampling error for a large number of samples. So these are the two things we do on the theoretical side for the adversary. And that means we also achieve a high accuracy gadget tester, because for proofs, if you are using some gadget, the gadget has to be 100% accurate. You are saying that's the sufficient condition for anonymity, that's your gadget. So even if this adversary produces even one counter example, that means the gadget fails. So that's the theoretical side. Now we actually decided to do, okay, let's actually try to use this adversary to evaluate a few protocols or figure out how it works on Mixnets. And actually, can we actually run some experiments on reasonable amount of time and get reasonable amount of guarantees. So for example, if the sampling error is too large, then probably you cannot use it. You have to reduce the sampling error to and then you have to make sure you are running enough number of experiments within certain amount of time. So first we did experiments on karaoke. We did show that the gadget is flawed through the experiments. However, even though their proof is incorrect, we showed that for a 14-hop networks and 20% compromised nodes in the network, still their guarantee is reasonably good. So something between order of 10 to the power 6, 10 to the power minus 6 and 10 to the power minus 7, which is not too bad, I would say. And another interesting observation was that the loss of privacy increases only sublinearly, not linearly, with the width of the network. That means if you are scaling for a high number of users, and for that you are expanding the width of the network, you are probably losing not too much. So you can, what you are losing, you can compensate that for with increasing the number of hops, but you don't have to increase the number of hops linearly. For Atom, we wanted to check if we could relax the square root in assumption and we could reduce the number of servers in the cluster. So we decided to do use cluster with 4 servers. And if you have 4 server cluster with 20% total compromise in the network, it's basically each cluster is compromised only with 2% probability, 2% chance. And even with that reduced number of servers in each cluster, still 10 layers of mixing provides strong guarantees. I didn't put the numbers here, exact numbers here, but it's actually much, much, much better than the numbers we observed for karaoke. And then immediately the total number of servers traveled by each packet is reduced by 1/8. Instead of 320, we are now 40. So that's a significant improvement. So that means there is a strong hope in this direction, and probably we can reduce the number of servers in each cluster further and number of hops further as well. How much time do you have? Okay. And then we also did some general experiments to see the trends, how Mixnets behave, not specific protocol, rather in general. Then we confirmed that yes, there is the actual measured anonymity guarantees are quite higher than the theoretical guarantees of anonymity trilemma. but also we confirm that, okay, there is an anonymity and latency trade-off for Mixnets, and leakage is generally significant for less than 5 ops. Except Atom, even for Atom, even for 5 ops, still you get pretty good guarantees because each cluster is like have 4 servers in it. So effectively, you're still 20 hops in terms of number of servers. However, this work I would consider as a first step towards this technique or towards this kind of measurements. Still, we do not capture notions that require evaluating properties for intent-dependent messages. For example, notions like relationship anonymity, or if there are leakage directly from traffic profiling, or how the user is behaving in terms of the user only becomes online in the morning or always sleeps in the night. So those leakages are additional to what we capture in our model. In future, we also want to continue analyzing more protocols. For example, Trellis, XRD, they have different kind of mixing strategy, and suggestions are welcome in this space. And eventually want to make it as a plug and play tool so that you can actually input your protocol specification to the tool, and then the tool can evaluate the protocol. That's the final goal, but we are currently far from there. Thank you, and any questions?
Thank you, Deb, for the great talk. Anyone with questions in the room? All right.
Do you plan to incorporate this with your other work, analyzing continuous mixnet?
I don't think we can support continuous mixnets yet. I don't know how to do the proof for continuous mixnets in this framework. Even other obstacle is right now the proof relies kind of on batching technique. Without batching, it's kind of artificial. How do you plug the protocol? So continuous mixnet might be far from where we are right now. That's a different kind of batching, not this kind of batching. Yes.
Since you're tracking the probabilities of the paths the different messages take, I guess it's the case that the reason you were still doing a random experiment, you're sampling the resulting guarantees, is because there's randomness in the corrupted nodes. Is that the thing that you don't know when you sort of randomly sample every experiment to 20% of nodes? Like if you knew the nodes that were compromised, then you wouldn't need to do any of this, and you just compute directly the probabilities at the end. Is that correct?
I did not understand the question probably.
I didn't understand when you had examples where you had probabilities explicitly computed. So why do you need experiments? And then you said that's the approach that you're going to take. So I didn't understand why you needed an experiment when you could explicitly compute the probabilities. But then you gave examples where you were showing okay, let's assume that 20% of the nodes are compromised. And then it seemed to me that what you're doing, the reason that you're doing these experiments is because you don't know which 20% of nodes are compromised. You're just assuming that it is, and so you need to randomly sample those, and then that's the thing that you're doing experimentally, is figuring out what the implications are of an assumption that there is X% compromised, but you don't know which ones.
Yes, exactly.
Okay, all right, thanks.
Right. To kind of follow up on that, do you have any sense of how bad an impact on poor sampling could be in this? Because it's possible that this particular space, you could imagine the sampling limits or somehow does not pick the worst case scenarios where all the malicious nodes are in fact on the path, right?
Yes.
So is there a way to gauge how poorly we could end up in this world?
For our purposes, we actually sometimes did experiments for 100,000 samples. So just to minimize the sampling error. So basically the sampling error is, I think, proportional to square root of number of samples. So yes, you can, if you only do it for few samples, you can end up in a scenario where the sampling is really bad and the error is actually not, you cannot bound the error. You cannot say anything about the bound is. Probably the bound is more than 1, then it doesn't make sense for probability. So it can be possible. And that is actually one of the reasons I don't think we should stick to entropy. We should move on.
Deb,
Thank you.
thanks for the great talk, and another quick round of applause for Deb.